All right, Kendrick, Joel, you guys ready? We can go ahead and get started if you are.
Ready?
Okay,
Awesome.
Great. Well, let me begin by welcoming everybody back to the SMU Physics Department Speaker Series for the fall of 2020. This event is a seminar, and the seminars are intended to dig deeper into the theme of the month, which is computing the cosmos. Now, in just a moment, Professor Joel Myers, who will act as the host for our speaker today, will introduce Professor Kendrick Smith. But before we get started, I just wanted to remind everybody, first of all, on Zoom, that in order to ask a question, if you're not a co-host or a host, you have to request permission to speak. And so to do that, you just have to type the word speak into the chat window in Zoom. And at the next available break in the talk, like at the end of the slide, we'll interrupt Kendrick and let him know that there's a question, and then unmute you, and you can go ahead and ask your question. Now, you're only going to be able to speak when you're called upon by a moderator and your microphone has been unmuted by a moderator. And I just want to remind everybody that this event is being recorded and simultaneously live streamed on YouTube. So to the viewers on YouTube as well today, welcome to this event. And I'm going to hand things over at this point to Joel now to introduce today's speaker.
All right, thanks, Steve. So we're very happy to have Kendrick today. Dr. Kendrick Smith is a member of the faculty at the Perimeter Institute in Waterloo, Ontario, Canada. He earned his second PhD in 2007 from the University of Chicago. His first was in pure mathematics from the University of Michigan. He then held postdoctoral positions at the University of Cambridge as a Science and Technology Facilities Council postdoctoral fellow. And after that, as a Spitzer postdoctoral fellow at Princeton University. From 2012 to 2013, he had a joint affiliation with Princeton and the Perimeter Institute. He currently holds the Daniel Family James Peebles Chair in Theoretical Physics, and along with the other members of the CHIME collaboration, he was co-awarded the 2020 Canadian Governor General's Innovation Award for innovations which are truly exceptional, transformative, and positive in their impact on quality of life in Canada. Dr. Smith is a computational physicist with interests in cosmology and radio astronomy, and we're very happy to hear from him today and about the CHIME telescope and its impact on understanding fast radio bursts. All right, go for it, Kendrick. Thank you.
Thanks, Joel. So the screen sharing is working, right?
Yes, indeed. Looks great.
Great. Okay. So I'm going to talk about the CHIME telescope, the project I've mainly been working on for the last few years, and especially the FRB science results from the last 2 years. So I'm going to start by acknowledging my collaborators. CHIME is a team of around 150 people. That includes everyone from people who design better amplifiers to people like me that work on software and algorithms. So CHIME is mainly a collaboration of between large teams at the institutions on the top and smaller teams at the institutions on the bottom, including Perimeter, where I'm based. In the first slide, I've just introduced CHIME at a bullet point high level. So CHIME is a compact interferometer with no moving parts, except for the Earth rotation, which is a universal moving part for every telescope that sweeps out the northern sky every 24 hours. It consists of 4 cylinders, and what you can't really see in this picture is that each of the feed lines running down the middle of the cylinder has been instrumented with 256 feeds or antennas for a total of 1,000 antennas. It observes radio waves in frequency range 400 to 800 megahertz, which was originally selected for cosmological reasons, but that happens to be a very interesting frequency range for fast radio bursts and other things, which is great. So far, almost all of our science results have related to fast radio bursts, so I'm going to focus on that in this talk. So I want to start by talking about the idea of CHIME, by contrasting the CHIME design to a traditional radio telescope, which consists of a feed or a few feeds suspended in front of a big steerable dish. The traditional telescope focuses by optical path delays. In the diagram shown, all of the when a bundle of rays comes in from infinity, the total path length to the feed is the same for all rays, meaning that the interference is constructive and the telescope is focused. If the bundle of rays were to come in from a different direction, then the constructive interference condition would not be satisfied, and you would not be focused on that part of the sky. Now I want you to imagine in this diagram getting rid of the dish and simulating it in software. And what I mean by that is that you get rid of the piece of metal and you replace it by a bunch of antennas, one antenna per square wavelength roughly. And then at each of those locations, the electric field is recorded and digitized. You can then perform an arbitrary computation, and in particular, you can add the electric fields with the same pattern of delays that the optical telescope would induce. So by summing these signals with an appropriate set of delays, you can simulate the dish in software and focus on part of the sky. And if you wanted to repoint, you would just change the pattern of delays which is applied. Now you may wonder what this gains, and what it gains is something very interesting, which is that because digital time streams may be copied without losing information, you can repeat the computation n times to focus in different parts of the sky. You're not limited to pointing in a particular direction. And you also gain the statistical power of n telescopes pointed in slightly different directions. Now, CHIME is an extreme case of this design, where we have 1,024 antennas and enough computational power to form all 1,024 independent beams in real time. And so our raw sensitivity is the same as 1,000 single feed radio telescopes, all pointing in slightly different directions. That statement might sound too good to be true, but it actually is true. I want to show some cartoons for how CHIME observes, which will be useful to keep in mind throughout the talk. So the so-called primary beam, or the sensitivity pattern on the sky that would be seen by any single antenna in the system, is shown on the left. The CHIME design is actually a compromise between optical focusing and software focusing, where the cylinder is focused in one direction, not the other. And so the primary beam is a strip running along the sky. By combining electric fields from multiple antennas and beamforming, or applying delays in software as previously described, we can focus on a 4x256 pattern of so-called formed beams within the primary beam. And this whole pattern of primary beam and formed beams is fixed in the coordinate system of the telescope, which has no moving parts. But as the sky rotates, we sweep out the northern sky. And the main science product from CHIME is an image of the sky made with the resolution of the formed beams, or around 1/3 of a degree, every 24 hours. Now, by background, I'm mainly a CMB cosmologist. And so I got, not a radio astronomer, and so I got interested in this project a few years ago when I was doing calculations like this. So from everything that I've said, and you might surmise, and this is mostly right, that the statistical power of a radio telescope is proportional to its mapping speed, which I've defined as the collecting area. That's setting the instantaneous sensitivity per beam, multiplied by the number of beams that you compute, times some order 1 factors that I've omitted in this back of the envelope comparison, things like noise temperatures, bandwidths, and so on. Anyway, with that back of the envelope definition of mapping speed, and in some weird units that no one actually uses, you can see that CHIME has comparable mapping speed, or better than, all of these famous radio telescopes, including, for example, FAST. But this next slide shows CHIME and FAST compared to scale, just to emphasize what a ridiculous statement that is. CHIME is one of the most ambitious projects in astronomy. It's a 500-meter telescope in China. And CHIME is, by comparison, a grassroots effort built on a few % of the budget. So this comparison seems too good to be true, but then the calculation on the previous slide seems too simple to be wrong. So what's going on here? So it turns out that there is a catch, and that is that the mapping speed you should really understand as being statistical power in principle under the assumption of infinite computing power. But the computational cost of the experiment is proportional to the number of beams, since that is determining the total data volume. Or maybe worse, for example, a brute force correlation between every pair of antennas has computational cost n beams squared. And in fact, radio astronomy already by reputation is one of the most computationally difficult areas of astronomy. So it's not obvious that the CHIME design is a step in the right direction. But it is much cheaper. If you just want to maximize M, the product of A and N, then it's much cheaper to increase N. Just adding antennas to an interferometer actually increases both A and N, and it's super cheap. Whereas making a dish bigger is really expensive. So the CHIME design is really a strategy for moving difficulty from hardware to software. We're saying we'll just build this really inexpensive instrument, at least by comparison to other projects, that has huge mapping speed and confront difficult problems in computation later. So computing is really central to everything that we do in CHIME, and so I want to talk a little bit about the computing backend. So the first thing that happens is that the analog signals go on coax cables to some FPGA boards that digitize and also do a little computation, break the signal out into frequency channels and rearrange it on the network. And the raw data rate, just to get a sense of scale at this point in the system, is 800 gigabytes per second. And when I give talks to astronomers, I like to convert that to astronomers' units and say that it's 5,000 copies of the LSST telescope, which is often described as big data in astrophysics. But radio astronomy is orders of magnitude larger than in computational volume than other areas of astronomy. The largest computational element in the system is the GPU correlator. If you're not familiar with the radio astronomy language, what's being correlated here are electric fields from each pair of antennas. So what the correlator actually computes is at a fast sampling rate every 2.5 microseconds, the 2-point correlation between electric fields at every pair of antennas. And that is much too large a data product to do anything with, even to send it out over the network. But it's a universal data product in the sense that anything that you would ever want to do with CHIME compute in CHIME can be derived from it. So we add capabilities to CHIME by building new software backends. And each block in this diagram is really like a cluster of computers that run different software that we wrote from scratch. So this is sort of like building a data center from scratch. And each of the science backends in this picture is asking the correlator for some different data product that can be derived from the visibility matrix. Sorry, the visibility matrix is the covariance matrix between the antennas. So the FRB search backend, for example, is asking the correlator at each of the 1,024 independent sky locations, what is the intensity or the squared electric field averaged over polarizations and with a little bit of time downsampling at a certain time sampling rate and frequency sampling rate. And the other backends ask for something different. The software that runs on the FRB search backend searches about a petabyte of data per day for fast radio bursts. And that's a very challenging computational problem, and the software had to be written from scratch by this group of people at Perimeter Institute. And so we sort of revisited this old problem of searching for fast radio bursts. I'll say more in a few slides about what a fast radio burst is and how we search for it. But our search algorithm is orders of magnitude faster than previous software, which was really necessary at CHIME data rates. And we also solved some additional problems, figuring out how to make it like an optimal matched filter. We run in real time with short latency. That's new, and it was necessary for CHIME because we can't save all of our data. We have to do a triggered search where you have to find, if you're looking for something, you have to find it when the data is still in a memory ring buffer and decide to trigger and save it to disk. Otherwise, the data leaves the ring buffer and it's as if the data was never taken. The most challenging part is removing RFI or human-made radio transmissions from the data. Humans make a ton of radio waves, like a cell phone a kilometer from the telescope is as bright as the sun. And so humans make a lot of radio waves, and they also make them in great variety. And classifying them and removing them, quickly in real time is a very difficult problem. Here are a couple of slides that I think are fun, so I left them in my talk. Here's some C++ code for computing the transpose of an n by n 32-bit floating point matrix. Now you might think that this code is too simple to be optimized, aside from testing which ordering of the for loops is fastest, which I already did. But here is a version of the code that's 4 times faster. And the way this works is that surprisingly in 2020, it's possible for the human compiler to beat the real compiler. If you learn how to use the so-called SIMD registers that hold multiple floating points at once, and you sort of learn the rules of the game, this code is transposing the matrix in 8x8 blocks by reading a whole 8x8 submatrix into special SIMD registers, and then shuffling the data around to do shuffling the matrix elements around to do an 8x8 transpose in memory. Now this pair of slides doesn't really do justice to the way we get large speedups. We get more of a speed up from revisiting the algorithms and finding algorithmic ways to make them faster. And I used to give a talk that was mostly about computation that went into the details of that. But since we now have so many science results, I prefer to gloss over it and talk about the science. But I left these 2 slides in because I'm just partial to them because I think they're fun. Okay, so for the rest of the talk, I'm going to talk about science. So I haven't really said what fast radio burst is, so I'll do like a little mini introduction for the next few slides. So very occasionally, as in a handful of times since initial discovery in 2013, a bright, short, highly dispersed radio pulse is observed. Dispersed means that the arrival time of the pulse depends on the frequency channel being observed in such a way that the delay is proportional to frequency to the -2. And that dispersion relation arises from and is interpreted as being due to a cold plasma of ionized electrons along the line of sight. The coefficient in the dispersion relation is very well measured. It is called the dispersion measure and is proportional to the integral of the electron density along the line of sight. So you get to measure this one number, which is counting electrons between you and the source, but you don't know where the electrons are. And around 100 FRBs have been reported so far since 2013. And at CHIME, we discover new FRBs at around 10 times the rate of all the other telescopes in the world. And we have about 1,000 unpublished so far. So when you observe an FRB, you don't get a redshift. There are no spectral lines in radio, at least in this frequency range. You just measure a dispersion relation, or a dispersion measure. But a few FRBs have been measured with enough angular resolution to uniquely associate the FRB with a host galaxy, which can then be followed up in the optical, say, and a redshift determined. And so with about 10 points in the redshift DM plane, it looks like FRBs first are usually at cosmological distances. And second, that the redshift is proportional to the dispersion measure, meaning that the dispersion measure is a reasonable distance indicator and most of the contribution to the electron density integral is coming from the intergalactic medium between us and the host galaxy of the FRB. And the implication of these cosmological distances is that to be consistent with the observed brightness, FRBs must be ultra energetic, like many orders of magnitude brighter than the brightest radio pulses that have been observed from known sources in our galaxy. And explaining the origin of these bright pulses has become, over time, I would say, a central unsolved problem in astrophysics. One thing I should mention is that some FRBs have been observed to repeat. So prior to CHIME a couple of years ago, there was only one, which became known as the repeater. And it was a real goldmine of information because if it repeats, then you can observe it with every telescope at every frequency. You know where to look, so you can just stare. And in particular, you can stare with a VLBI, or very long baseline interferometer, and get the angular resolution to localize it to a host galaxy. In the first year of our operation, CHIME found 18 new fast radio bursts. Since then, two more have been found by other telescopes, and we also have a few dozen that we haven't published yet. It's an open question in the field whether all FRBs repeat, or whether repeating and non-repeating FRBs are different types of objects. Something analogous turned out to be the case with, I should say, with gamma ray bursts, which are a similar puzzle from 40 or 50 years ago, where there were two types of gamma ray bursts, the so-called long duration and short duration gamma ray bursts. And a lot of theoretical energy was spent trying to explain them both with a unified model, but they turned out to just be different types of objects. And so something similar may prove to be true for FRBs. For what it's worth, at a recent FRB conference, about half of the polled conference participants felt that all FRBs repeat, and about half thought that the repeaters and non-repeaters were probably different types of objects. I guess my conclusion is that no one has any idea. Here's my theory slide, which is super lame, which is to say that I just want to make the point that explaining FRBs has proven to be such a difficult problem, and there have been so many models proposed by theorists that people have started writing papers like this one just to keep track or catalog all of the different theories that have been proposed for FRBs. I won't really, I won't really get into the details of any of this, since I'm mostly going to talk about observational results from CHIME. It used to be the case that it was sort of impossible for me to keep track of all these different models or know which ones I should be paying attention to, because it's a full-time job, and I have a different full-time job. But I think that that's not true anymore with the observation of the galactic FRB that I'll talk about later. The theory landscape has really shrunk a lot. Now I'll move on. So with that brief mini introduction, I'll move on to the science results from CHIME. As I see it, this list are the most important science results we've published, or the highlights. So I want to start with the statement that FRBs are ubiquitous at low frequencies. So this is still a bit of a puzzle. So we found these 13 FRBs are from a paper that we published a month after first light, when we didn't really expect to be detecting FRBs. And in fact, CHIME at this point was in kind of an evolving debugging state, where we were fixing problems and installing new nodes even. And we didn't really expect to be finding FRBs during this time, but they just started popping out as soon as we got the software working and got things plugged in. So prior to these observations, almost all FRBs had been detected at 1.4 gigahertz versus our frequency range from 400 to 800. And so one of our risks was that FRBs would be absent, or at least rare, at our low frequencies. And this didn't prove to be the case at all. In fact, we don't even see a preference for FRBs being harder to find at low frequency. If you look at our sample, about half of them are brighter at the low end of our band, and about half of them are brighter at the upper end of our band. So it's very puzzling that still to this date, all FRB searches at 200 megahertz or below have been unsuccessful, suggesting that there's some sort of spectral cutoff. But I think it's very difficult to get a spectral cutoff in a model, right? If radio pulses are due to accelerating electrons, then that process just doesn't produce a spectral cutoff. And other astrophysical mechanisms for suppressing the spectrum along the way, like free absorption, really can't produce a sharp cutoff either, especially if they happen in the source frame of the FRB. And the FRB is at a cosmological redshift, so you're forced to convolve with the redshift distribution. I sort of, for a long time, have been assuming that the searches at low frequency have just been unlucky. But this statement is held up that FRBs appear to be absent below 200 megahertz. So I'm really just not sure what's going on. In our first month of data, we also found the second repeating FRB. And since then, we've published 18 repeating FRBs. Now, one thing I should mention is that it is a bit of a judgment call in deciding whether a whether a radio pulse is an FRB or whether it originates in our galaxy. So what we do, by definition, an FRB is extragalactic. So what we do is we observe the DM or dispersion measure of the FRB, and then we compare that with the total number of electrons along the line of sight if you integrate to the edge of the galaxy using a model for the electron distribution of our galaxy. And the models are very complex and include things like ad hoc regions, ionized regions of free electrons to account for the observed dispersion measure patterns in pulsars. So in most of these cases, the observed dispersion measure from our FRBs are much larger than the predictions from the galactic models. So the extragalactic nature of the pulse is sort of unambiguous. But from this list, I think, at least when our paper came out, I thought that R3 and R4 were sort of borderline. For example, R3 has a total dispersion measure of 350. And there are two models for the galaxy in common use, one of which predicts a galactic contribution of 200, which seems pretty safe. And the other predicts 325, which is super iffy. Since then, we have learned that R3 is, in fact, is definitely outside of our galaxy, as I'll explain in a few slides. So this allowed us, the observation of more repeaters allowed us to test whether certain features noticed in the original repeater were common or unique. So one thing that turns out to be common is this so-called downward marching frequency structure. So you can see that the radio pulse for many repeaters is not just one pulse. It consists of a sequence of subpulses that sort of march downward in spectral in radio frequency. And different models try to explain this in different ways. For example, if the in some models, the FRB is due to some electrons that are ejected from a central engine, like a magnetar, and then crash into like a surrounding, crash into some surrounding free electrons, like in the supernova remnant, and shock, and that's where the FRB is emitted. And in these so-called outflow models, what might happen is that there are multiple shocks, and in between the shocks, the electrons lose energy, which leads to this this downward frequency, downward marching structure. So we see this in many of our repeaters. Another interesting thing that we can start to do with statistical samples is look for differences between the repeating and non-repeating populations. And one very striking difference is that they have very different pulse widths. Repeaters have wider pulses than non-repeating FRBs. The histograms are shown here, and the two histograms are obviously different, and the formal significance is something like 4 sigma. One of the most interesting papers about the original repeater showed that it inhabited an extremely magnetized environment. And as far as we can tell, that's sort of unique and doesn't occur very often. So I should explain that the way that magnetization is inferred from observations of the radio pulse is, well, first you have to capture the electric field from the event, which we don't always succeed in doing for technical reasons, but here's an example of a pulse where we did. And if the electric field is recorded, and if the pulse is linearly polarized, then a magnetic field along the line of sight will rotate the direction of the linear polarization as a function of observing frequency. This is the so-called Faraday rotation effect. So with this definition of the rotation measure, or RM, this particular event and the other pulses that we've reported have a modest rotation measure, which is consistent with being due just with the magnetic field of the Milky Way. Whereas the original repeater had a huge value. It's one of the most magnetized objects on the sky. suggesting a highly magnetized environment. The next couple of highlights will specifically concern the repeater R3, the second repeater found by CHIME, and the third repeater found ever. So this is the most active repeater in CHIME, and it turned out to be super interesting for several reasons. So the low excess DM, as I explained earlier, that's sort of a bad thing, since it means that it's hard to be 100% confident that it's really extragalactic. But if it is, then it's at low redshift. However, the CHIME angular resolution, even if you restrict the search to very low redshift galaxies, is not quite good enough to uniquely identify a host galaxy. So what we're currently doing in CHIME is like outsourcing our VLBI. So we partner with the European VLBI network to observe many of our known repeaters. So they stare and see if we tell them where to point, and they look and see if the repeater goes off again. And in the case of R3, it did. The EVN observed 4 pulses. And the EVN is spread out all over Europe, so its angular resolution is amazing. It's more than good enough to identify a host galaxy, which turns out to be this spiral galaxy at redshift 0.03. And the EVN resolution is even good enough to pinpoint where the FRB went off in the galaxy. It went off in like a little star-forming knot shown in the upper right of the plot. And so this is the closest FRB found so far, which makes it a natural candidate, and it repeats, which makes it a natural candidate for follow-up if you are hoping that FRBs are associated with emission in some other frequency range, say in X-ray or gamma rays. Then looking at the closest FRB is a good strategy, or would seem to be a good strategy. I should say that it would be a huge milestone if anyone associated an FRB with emission in some other frequency range. Something super interesting about R3 that was just a qualitatively new phenomenon was the observation of periodic activity. So this plot explains what I mean. So CHIME, remember that in the CHIME observing strategy, we observe every location on the sky once every 24 hours. And the red triangles in this plot show the days when we observed pulses from R3. The numbers are showing the number of pulses that we observed. And the gray bands are not something that's directly observed. We just noticed that if you set down an array of gray bands with a particular spacing, that we only see pulses during the gray bands. So I want to distinguish between periodic activity, which is what we observe. It means that only during a certain periodic window is the FRB allowed to be active. But I want to distinguish that from strict periodicity, which is like the ticks of a clock, where we see some periodicity in the arrival time of the pulses, or what you see for a pulsar. As far as we can tell, when R3 is active, the pulses don't follow any particular periodicity, but the times when it's allowed to be active are periodic. Now, the first question you might ask is what is the statistical significance, whether this could be a statistical fluke. And so I've done sort of an order of magnitude version of the calculation here. The gray bands are 4 days wide. So the probability that one of the red triangles would be inside the gray bands by chance is 4 over 16.35. And there are 11 red triangles, so I raised that to the 11th power. And then that doesn't account for the look elsewhere effect, or the fact that there were many trials in the ways that I could have set down the gray bands. And so the associated trial factor there turns out to be about 270. I've omitted the details of the counting, but that's roughly the number of independent ways of setting down a periodic array of gray bands in the plot. And that gives a p-value, or a probability that this periodicity is a statistical fluke, of around 5 times 10 to the minus 5. So it's a very statistically significant detection. Now, the next question you might wonder is whether this can be an instrumental effect. So the way that we convince ourselves that it wasn't is by searching for a comparable periodicity in different instrumentally derived quantities. So if we take, for example, our exposure or some measure of our sensitivity, like noise level, as a function of time, then we don't see any feature at a period of 16.35 days. And we also don't see any feature which is nearly as large as the periodicity that we observe in R3. Another great instrumentally derived quantity is the number of pulsars that we successfully detect on a given day. I like that a lot because it's sensitive to things like the amount of RFI in the environment. We also do things like make discrete data sets by taking random subsamples of galactic pulses that have the same number density as the same total count as the number of pulses that we observe from R3. And in none of these cases do we see a statistical feature, a random feature that's anywhere near as large as what we see in the data, or any preference for a 16-day period. So this observation would seem to be super solid, except for one interesting loophole, which we didn't notice in version 1 of our paper until it was pointed out by our colleague, Shami Chatterjee. And I like talking about it because it's something that I think you only need like freshman physics to see the loophole, but like 100 professional physicists failed to notice. So if there are any students listening, you should view the statements by your senior colleagues with occasional skepticism. Sometimes we don't really know what we're doing. Anyway, here's the loophole. This plot shows a representation, a cartoon representation of our data. So the x-axis is time in days. And a key detail of the CHIME observing strategy is that we observe only at integer values of t. We observe every 24 hours exactly. The red points are the activity level that we observe in R3 in some arbitrary units. Now, if this is your data, it's natural to connect the red points by this blue line and infer a 16.35 day periodicity. But whenever you observe a periodic signal with periodic sampling, there is the issue of aliasing. And you could just as well connect the red points by this curve, where I've just advanced the frequency of the blue curve by 1 inverse day exactly, or any integer number of inverse days. The blue curve and the purple curve cross at integer values of t. That's an exact statement because I've just advanced the period of the period of one curve by 1 inverse day relative to the other. And we'll continue to do so forever. We can never tell the difference with CHIME for as long as we observe. And so we now we amended our paper to say that this doesn't affect the statistical significance of detecting periodicity, but it means that we don't know which period we've actually observed. If we invert the period and express it as a frequency, then the period is 1 over 16.35 plus some integer. The upper bound on n here is related to the fact that we don't observe for 0 duration, we observe for 10 minutes. And if the period were too fast, we would see the period would be smaller than our observational window and we could tell. And now we'll never be able to break this degeneracy, but a single contiguous observation from another telescope with comparable sensitivity like GBT could determine the true period and tell which of these alias solutions is right. Next, I'm going to talk about what I think is the most interesting result in FRB astrophysics since discovery of the original repeater, I would say, which is a giant pulse from a magnetar in our galaxy that is very plausibly an FRB going off in our galaxy. As context, FRBs are many orders of magnitude brighter than the brightest pulses ever observed from neutron stars and brightest radio pulses ever observed from neutron stars in the Milky Way. And that gap in energy is the reason why FRBs are such a puzzle in the first place. On April 28th, CHIME observed 2 pulses from a node magnetar with an energy that closes most of this gap. So the energy is 3 times 10 to the 34 ergs, which is closer to the faintest FRBs than to the brightest previously known pulses from neutron stars. So CHIME actually observed 2 pulses, as shown in the lower left. And the first pulse was also observed by the Algonquin radio telescope. And the second pulse was also observed by the STARE-2 experiment, which is based in Caltech. So this closes most of the energy gap between galactic pulses and FRBs. Here's a plot showing a bunch of different pulse types separated out by pulse duration and luminosity, energy per second. And the known pulses from galactic pulses from like neutron stars in our galaxy are represented by the orange cluster of points in the lower left. The brightest pulses from those objects are giant radio pulses, or GRPs, and they scatter a little higher in energy. But they're still nowhere close to the FRBs, which are shown in the upper left. And this radio pulse is indicated with the black star. And it's not quite as bright, but it's close to the faintest FRBs that have been observed. So this is very plausibly an FRB if you're grouping radio pulses into categories. It makes more sense to associate this pulse with the FRB population than it does with known pulsars. Now, one of the most interesting things that have followed this observation is the comparison between X-ray activity from the magnetar and the giant radio pulse that we saw. Several X-ray telescopes observed X-ray pulses. I should say that this magnetar is also very frequently active in X-ray that are coincident with the radio pulses. And something that is super constraining for models is the arrival time lag between the radio and the X-ray. So I'm going to define this the lag L to be the arrival time in radio minus the arrival time in X-ray, with the sign convention that positive L means that X-ray arrives first and the radio arrives second. As far as I know, the magnetar models, there are many different types of models that try to explain FRBs using magnetars somehow. As far as I know, they all predict that the lag is greater than or equal to 0. But some of them predict that it's like a lot bigger than 0, and some of them predict that it's very close to 0. So it was very puzzling that the first X-ray experiment to report results found arrival times where the radio pulse arrived first and the X-ray pulse arrived second. In other words, the value of L was negative. And this has been so puzzling for the theorists that when I was preparing this talk, every theory paper that I looked at interpreted the integral paper as saying that the X-ray and radio pulses arrive at the same time. But the plot has thickened somewhat since, which I think is not a completely fair interpretation. But the plot has thickened somewhat since other X-ray experiments have reported results. So since then, 2 other X-ray telescopes reported timing results for these 2 pulses. The InSight experiment reported arrival times that were consistent within statistical errors of the original InSight results. Taken in combination, increased the statistical significance of negative L to 8.5 sigma. But there was another experiment called CONUS Wind, which reports arrival times that are look very similar to the radio arrival times. Sorry, I should back up and say that the blue points in this plot are the radio observations, and they do have error bars that are plotted by the plot script, but the error bars are smaller than the widths of the point. The statistical errors in radio are really tiny. The X-ray experiments, so I showed error bars for the integral and InSight experiments, but the CONUS paper just reported timings without reporting statistical errors on those timings. And When I read their paper, according to my reading, it's because they kind of reported arrival times as a little bit of an afterthought. The main focus of their paper was on the energy spectrum of the pulses. So without statistical errors, it's hard to interpret those measurements. The interpretation depends on what you think the statistical errors are. If you think the statistical errors on the CONUS points are comparable to the other experiments, then I would conclude that there's just some undiagnosed, that the scatter in X-ray measurements is just larger than the statistical errors, and there's some undiagnosed systematic error floating around. But if the statistical errors on the CONUS points are large enough to be consistent with the other experiments, then I would say that it's pretty convincing evidence for negative L, which would be super puzzling. So for what it's worth, the instrumental time resolution of CONUS is comparable to InSight and much better than integral. If these observations of negative L hold up, then it'll be really puzzling in the sense that these observations do suggest that FRBs are magnetars, which would really narrow down the theory model space, but would also rule out every model that's actually been proposed to explain FRBs with magnetars. So we'd go from a situation where a few years ago there was just this huge unconstrained landscape of models to a situation where every model has been ruled out. But this is an evolving observational picture, and we'll see what happens. So it's tempting to speculate that all FRBs are magnetars, since I personally think that it's pretty convincing that we've seen an FRB in our galaxy, and that FRB is a magnetar. There are a couple of the next step is to wonder whether, it is indeed true that all FRBs are magnetars, or whether there are multiple FRB populations and magnetars just account for a subpopulation. So as sort of cautionary notes toward this interpretation, one thing I should say is that of the FRBs that have been localized to galaxies, some of them have been found in places where you wouldn't really expect there to be a magnetar, like the outskirts of a galaxy. For example, the CHIME FRB that's been localized, R3, is in the outskirts of a spiral galaxy. And that is, given the distribution of magnetars in our galaxy, that would be sort of unlikely. But I think it's hard to say with only one object. With one object, there are bound to be a few sources of tension at sort of borderline statistical significance. A similar cautionary note is that the morphology of the SGR 1935 double pulse would be fairly atypical for an FRB. What we see in the galactic magnetar is a double pulse which is marching upward in frequency. And as stated earlier, what we typically see in FRBs is a downward marching frequency structure. But that's actually not the case 100% of the time. So in the middle panel, I showed a downward marching pair of pulses, which is very typical. And in the right panel, I showed, and this is even for the same object, R3, a pair of pulses which are upward marching in frequency. That happens like some fraction of the time, like maybe a few percent. So this is another situation where I think, it looks like there's some tension, but the statistical significance is inconclusive, and we just need more observations. We need more galactic FRBs. There's a great observational strategy for seeing more of these galactic FRBs, which is to look at nearby star-forming galaxies. And I imagine a lot of people are doing this. For example, M82 is a great place to look. When the magnetar went off in our galaxy, it was incredibly bright, like it totally saturated CHIME, and it was observed at incredibly high signal to noise. And if you were to put that same FRB in M82, then it would be bright enough to be detectable with, say, a 20-meter telescope. You wouldn't need something like CHIME or GBT or anything like that. But you should see, rather than having to wait for 2 years, as we did in CHIME, you should see them rather frequently, since M82 is a larger galaxy. It has something like 40 times the star formation rate of the Milky Way. Presumably, the rate for giant magnetar pulses is related to the star formation rate. So I imagine that a near-term direction in the field will be to detect a bunch of these pulses from nearby star-forming galaxies and sort of build a bridge between this one event that we've seen in our galaxy and this population of FRBs that we've seen at cosmological distances. And that'll just be super informative. We'll have two populations to compare and see how well they agree.
Kendrick, I just want to interrupt you for a second. We have a question from Bob Kia. So,
oh, yeah.
Bob, go ahead and try to unmute. And if you can't, wave your hands at the camera. Did that work? Oh, good.
Okay. You can hear me?
Yes.
So yeah, it's interesting. This really sounds very similar to the gamma ray burst situation. I had a question. In this, are you able to make any general comments about the rate of multi-wavelength counterparts to repeating versus non-repeating FRBs? And I'm particularly interested in the optical, but I have a follow-up question. But yeah, are you able to? I mean, maybe you don't have enough events, but are you able to make any comments?
Oh yeah. So for cosmological FRBs, there have been no successful multi-wavelength associations. We just have upper limits. So
even in X-rays.
Oh yeah, that's right. So observing an FRB, a cosmological FRB multi-wavelength would be a huge milestone. Now, so the only case where we've made a multi-wavelength observation is this galactic FRB, which was also active in X-ray.
Well, I had thought that there was a gamma ray burst that overlapped an FRB also.
Oh, there was a claim like that, like
2018, 09, 16, I guess.
Oh yeah, that's right. My understanding is that I have to admit
But that one was probably gamma ray, so not optical though. That was probably gamma rays or X-rays from the gamma ray.
Yeah, that's right. I haven't looked at that in a while. I think that's not generally.
Well, the follow-up question really is because you brought up the point about short and long duration gamma ray bursts, and of course, one of the distinguishing factors eventually became that the short bursts, there's not nearly the optical signature that there is for the long bursts because there's no material there, and you're bringing up this area about whether they're in the star-forming regions, and I just was wondering if there was enough information to start guessing there, but it sounds like it's still too little information to say.
I think with more, yeah, right now, there just isn't multi-wavelength information available for cosmological FRBs.
Are there a lot of, I'll shut up after this, are there a lot of collaborations trying to do follow-ups of, say, CHIME triggers or things like that?
Oh yeah, it's not for like lack of looking.
Yeah.
A lot of people have looked, and there are a lot of upper limits.
Yeah, interesting. Okay, thanks.
Sure. Okay. So the last thing I want to talk about is forthcoming stuff that's happening in the next few years. So you probably noticed that throughout the talk, I kept talking about all of the wonderful observations we had that weren't published yet. And the things that were published were mostly, sort of one-off statistical things, like a modest-sized catalog of repeaters, the galactic magnetar, the periodic FRB. But we have, some on the order of 1,000 FRBs that we haven't published yet. And the reason that this is taking so long is that, a large catalog is a wonderful opportunity to do population statistics. But it also means that you have to understand the instrumental selection very well. Like if you just do something like plot a histogram of the energies of the FRBs that you've observed, then that's not straightforward to interpret, since you have to divide out the probability that an FRB of a given energy was bright enough for us to see it. And modeling the selection of a complex instrument by CHIME is very difficult. And especially since our software includes, things like machine learning classifiers that are hard to characterize analytically. And so our approach has been to do real-time injections of simulated FRBs. We have like a little injection server that will place into the time streams that are being processed by the real search a simulated pulse, and let it go through all of the logic, the RFI removal, the machine learning classifiers, and then just fish out at the end whether it triggered or not. And so we get sort of a probabilistic Monte Carlo characterization of our selection function, which I think is the only way to do it. And so we've made a lot of progress on this, and many of the conclusions of our population modeling are in place. And I hope that this paper will come out on the time frame of, I want to say, a couple of months. Now, if you imagine that, here's something that I'm really excited about. So if you imagine that the power of an FRB finding instrument comes down to two parameters, the rate of detecting FRBs and the angular resolution, so CHIME is definitely the most powerful instrument in the world in terms of total rate. But our angular resolution is limited, and that means that we can't do things like associate FRBs with individual galaxies, except in cases where, this one case of R3, where we were able to partner with the European VLBI network. But there's a solution to this, which is to build outriggers for CHIME, which is something that has been very generously funded by the Moore Foundation and recently the NSF. So we're going to build like miniature versions of CHIME at Algonquin Radio Observatory in Ontario and at the Green Bank Observatory in the US. And a technical point to emphasize here is that normally VLBI is very expensive because you either have to connect the stations with optical fiber, which is obviously impractical here, or record all of the data to disk for online analysis, which would also be impractical at our data rates. But for FRBs, there's a trick where the outrigger telescopes are just sort of like dumb devices that keep their data in a memory ring buffer. And then because we already detect FRBs in real time in the core, when the CHIME core detects an FRB, it just sends a packet to the outrigger telescopes, telling them to dump their data to disk, or even like a very small subset of their data, since we know exactly what time and dispersion measure to use in real time. And then the data gets saved to disk, and we can bring it later together on like a traditional supercomputing facility to do the VLBI analysis. So when these outrigger telescopes are complete, we'll have the best of both worlds. We'll have the CHIME event rate together with just exceptional angular resolution that will something like 50 microarc seconds, I think, is probably realistic. So this is in progress and should happen in another, I would guess, 18 months or so. We're also building a sequel experiment to CHIME called CHORD, which is just, it's really the same philosophy as CHIME. We've just had a lot more time to polish things, and we're making incremental improvements in a lot of directions. We're widening the frequency range that we search, which will enable some new science, like that these high frequencies are really interesting for pulsar timing, for example. Lower noise, we're switching to dishes instead of the cylinders. We'll have more collecting area. Collectively, these improvements will increase the mapping speed by something like a factor of 8 compared to CHIME. And CHORD will have outriggers from the beginning. So I think that this new large N interferometry with new powerful software has become super interesting in the last couple of years. We've been able to scale up by orders of magnitude compared to what we've done before. And we'll be scaling up by another order of magnitude, hopefully, in the next few years with CHORD. And there's just room to keep going after that. So this has been very exciting for the last couple of years, and will continue to be exciting in the future. Thanks, everyone.
Okay, no, thank you very much. And people can hit the applause button in the participants window. We'll try to give you some applause here, Kendrick. Excellent. All right, so we have some questions here. Krista Smith, go ahead. Let me make sure you've Find out where you floated in the menu here. There we go. Okay, go ahead. You can speak, Krista. Sorry about that.
Okay, yeah, no problem. Hi, Kendrick, thanks. I wanted to ask about the repeating bursts, whether you could comment on how similar the frequency morphology is for the repeating bursts to, I mean, when a burst repeats, does it have the same kind of drift and dispersion as the other bursts for that same object, or does that also contribute to this kind of wide histogram of burst durations?
Oh yeah, right. There's lots of details that I had to gloss over, but you can see if you compare, let's see, I want to show two slides again. Unfortunately, I can't show them at the same time, but so I showed this slide with 18 repeating FRBs. And then I showed this slide with 13 non-repeating FRBs. And so it is quite striking how the repeating FRBs have more structured pulses than the non-repeating FRBs, even without sort of incorporating the downward marching substructure. So, for example, the repeating FRBs, none of the pulses in this plot span the whole chime frequency range from 400 to 800 megahertz. They're all sort of narrow in frequency space, whereas these 13 FRBs, you know, about half of them span the whole span the whole frequency range. So that's something that we haven't commented on yet or quoted a statistical significance, but it's very clearly, even from the sample, you can see that it's very clearly a real difference. The pulse widths distribution that I drew was, you know, that was the width of the individual subpulses here, right? It wasn't grouping the subpulses together to compute a width. So there's some like, you know, even the repeating FRBs are different in I would say at least 3 ways. They span a narrow frequency range. They sometimes consist of multiple subpulses, and the pulses or individual subpulses are wider than the non-repeating FRBs. As part of our forthcoming catalog paper, we're going to talk in more detail about the differences we've noticed between repeating and non-repeating populations, and quote statistical significances for things. But it is quite interesting that there really is some sort of like bimodal structure in the FRB population where many things are correlated, whether an FRB repeats, pulse width, pulse narrowness, and so on.
Does that answer your question, Krista, or did you have a follow-up?
No, I have a completely different question, but I will wait and see if anybody else has one.
Okay. Yeah, Joel had requested to ask a question, so we could go back and forth there if that's okay.
That's fine. Yeah.
Yeah. Okay, Joel.
Yeah, thanks, Kendrick. That was an excellent talk. I think you actually touched on this in your answer to Krista's question. I was going to ask where you would come down on the poll of whether all FRBs repeat, especially with what you know about the data that you guys have in the can. But I think you sort of already tipped your hand on where you might come down based on that data. But I invite you to comment on that.
Yeah, I mean, I think it's. I wonder if it's a question that will ever be like conclusively settled. I guess if the story turns out to be similar to gamma ray bursts, where there really are just 2 types of objects, then it can be settled. But if it turns out that there's just 1 type of object and they repeat a lot when they're young, and they repeat rarely or not at all when they're old, say, then it might be. I guess we would eventually see that the gap between these populations closes, maybe. But I don't know. We might be stuck with bimodality forever and just be scratching our heads as to whether there are 2 types of objects or not. That would be kind of sad. I suppose.
Or an opportunity of some kind, perhaps. Sad may be the wrong word long term, but all right. So, Krista, did you want to ask your next question, and then we'll go to Bob for the last question here. So, Krista. Oh, sorry. Let me unmute you, Krista.
Okay. I guess that's the official distress symbol for I can't unmute. So
I love it.
So I saw a talk on CHIME FRBs a couple years ago at the AAS. I don't know if it was you or not, but I remember taking down the link for the Wikipedia or the wiki page of theories of what FRBs could be, because I was really fascinated by this. And I know you said, it's interesting that this galactic magnetar has excluded, well, if it's generalizable, has excluded a lot of models. But could you comment on the kind of fall off of those models over time? Because back even in 2018, the highly magnetized environment of one of the FRBs, like you commented on, that was being used to support a lot of these ideas. And as you said, another FRBs weren't highly magnetized. The host galaxy distributions, like obviously this has all changed completely since CHIME got really rolling. So how many of those are, like, percentage wise, are just dead?
Yeah. So it's interesting that you bring up the magnetized environment of the first repeater. I guess that's a classic astronomer's mistake to overgeneralize from a sample size of one, which I totally did in my talk by drawing sweeping conclusions from the one galactic FRB that we've seen. I would say that that's really the problem, that with individual objects, individual observations, and not enough objects to do statistics, then it's hard to reach strong conclusions. Like, we don't know if you decide that you think that all FRBs are magnetars, which is sort of what the observation of the galactic magnetar suggests. Let me also say that the rates are very consistent. If you just sort of extrapolate FRB rates down in energy a bit, then you would predict that you would see one FRB every few years in our galaxy, which is what we saw. We saw one after 2 years. Then a whole bunch of models are ruled out. The magnetar models are a modest fraction of the total model landscape. If you think that this observation of negative L was real, then all of the models are ruled out, as I was saying. Although I should add that I have no doubt that theorists are creative to come up with magnetar models with negative L. It just hasn't happened yet. It didn't happen before the observation. I think
desperation will force their hand, right?
Yeah, you should never underestimate the creativeness of theorists to come up with exotic models. So I think we're kind of in a transitional period where the landscape is narrowing rapidly. My gut feeling is that this, like gamma ray bursts, will eventually be a solved problem. That maybe the observations are really coming quickly and really narrowing things down a lot. And a few years from now, it wouldn't surprise me if FRBs were considered to be an understood phenomenon.
Okay, and our last question will come from Bob again. So let me ask you to unmute there, Bob. You should be able to do that now. Great.
Yep. Okay. Yeah. So this is kind of a follow-up on my earlier question, but maybe it's unfair too. I'm not sure how you can answer it effectively, but so back to the issue of no optical counterparts, and I guess the cosmological FRBs. Do you think that those observations are sensitive enough to demonstrate that there isn't optical emission, or do we still have a ways to go? And depending on your answer, do you start to think that that's supporting information to your idea that they're all magnetars?
So I don't actually know whether magnetars are emit in the optical. I don't think so, right?
Yeah, exactly. Yes, I don't think not like some things would do. They don't have big afterglow type behavior, unless, well, yeah, I shouldn't generalize too much, but so my question is the evidence there suggesting to you, since there aren't optical counterparts, that that's consistent with being a magnetar, or is it still that we don't have the sensitivity? We're not seeing, dim enough, deep enough to see any optical emission that might be coming out.
Yeah, I think a challenge for optical is the time resolution. FRBs are like a millisecond long. So if you have an optical instrument that's averaging over much longer durations for that, than that, and assuming that the optical, if there is an optical counterpart, it's also a millisecond, then you're losing.
Yeah. So in the gamma ray burst case, long duration gamma ray bursts last a few seconds. The optical counterpart lasts much, much longer than that. So if it was in a star forming region and it was something massive that wasn't like a magnetar, maybe there would be some sort of afterglow like that. But yeah, certainly you wouldn't have any sensitivity to a millisecond optical burst, probably.
Right. There was a ZTF paper recently following up R3 that didn't. I mean, they have.
Following up that one in particular.
That's right. Yeah.
Okay. Interesting. Okay.
Okay. Well, thank you very much.
Interesting talk and a lot of food for thought.
Yeah, I could not say that better. That's a perfect ending, Bob. Thank you. Yep. So Kendrick, thanks again for sharing your expertise with us. And this was indeed a great talk. And we're going to go ahead and close out the seminar right now and wish everybody a healthy and safe evening. And thanks again, Kendrick. Thank you very much.
Thanks, everyone.
Thanks a lot.
Okay. Bye-bye.
Bye.